our awesome speaker is Magdalena Stenius. She is a machine learning engineer in Valohai. So Magdalena, a little bit about Magdalena herself. She is an active member of the Finnish Women and Non-Binary Programs community, programmers communities, as well as the co-host of Taku.py is her hometown's local Python meetup. So she's been doing amazing works on her local community as well. She's very passionate about environmental topics and fairness in the context of machine learning and artificial intelligence. So that's a little bit about Magdalena, and I will hand it to you to start speaking the topic.
Okay, thank you, Karen. Awesome to see all of you here. As Karen said, my name is Magdalena, and today I'll be presenting about a topic that I'm myself very passionate about. And I'm trying to give a very practical approach so that all of you working in different roles, maybe technical, maybe non-technical, in the field of data science and machine learning, can take something away from this talk and implement it in your everyday work. So firstly, a little bit about the why. When I grew up as a child in Finland, it was already a big topic how we are in a climate crisis. As school children, we were always taught that we should save water by closing the tap after we're done using it. And we were recycling all the waste in the school as well. And we were taught that we should never be leaving the lights on in the classroom when we're leaving the room. And now the generation that has been learning this in school is now entering the workforce, and we can see how companies are more and more looking for answering to consumers' needs, and consumers want to see this increased transparency in the field of environmental impact, as well as companies also using environmental issues as their own guiding values to design products that are more friendly and more sustainable for the planet in the long run. And one of these examples is, for example, that I was talking with my friend who is a data analyst at one of the big car manufacturers in Europe, who are aiming to produce completely climate neutral, carbon neutral vehicles, electrical vehicles. And as she's working as a data analyst, she was saying to me that it's interesting that their team is looking for products or tools that can completely calculate their environmental impact while they are working with them. So she was saying that they would like to have some kind of machine learning tooling as well that could support this kind of measuring of the environmental impact, so that these products can be produced which are completely carbon neutral. And from this, I started looking into the environmental impact of machine learning and deep learning, especially because I work with this on a daily basis. So I was interested in the topic and what it has to offer. According to MIT's technology review in 2019, these deep learning models especially can consume, the training of these models can consume up to as much or can produce as much carbon dioxide equivalent as 5 cars during their entire lifespan, which is a lot. Just as a reference, one car emits around 300,000 kilograms of carbon dioxide equivalent during its lifetime. And here are some of the examples from this article. You can see that these are especially deep learning models focusing on natural language processing. And along with these staggering amounts of carbon dioxide emissions, you can also see that the cloud compute cost of training these models becomes greater and greater the more environmentally heavy the impact of training them is. And from this, we come to my second thesis of this talk. If you're not convinced about the idea of saving the planet or kind of building a sustainable future, you're probably at least interested in saving money. And this is also why green software and green code has become one of the very hot topics in the previous years. Just a few months ago, Helsingin Sanomat, which is the main Finnish newsletter, published this article about one of the Finnish main bus companies that were able to reduce the cost of their IT systems by 400,000 euros per year, just by optimizing their code base and renewing their IT systems. And you can imagine that this kind of optimization not only saves a lot of money every year, but also reduces the environmental impact of these software systems drastically. So one of the main topics of green software has been renewing, optimizing code and infrastructure. Another example was that the Finnish television company Yle did infrastructure optimization project where they set out alerts for infrastructure that was being underused. And in this way, were able to reduce their carbon footprint of their infrastructure drastically by, for example, removing instances and computers and storage that was no longer needed. Another topic that has come to the news has been the choice of programming language. For example, you can say that Perl, the programming language, consumes 80 times as much electricity as C. Of course, this doesn't mean that we should only be coding in C, but this is an interesting thing to think about or keep in mind when you're designing new systems. And also in the world of web development, the transfer of data and optimizing the transfer data, for example, optimizing image size and topics like this have become a hot topic in kind of making your software more environmentally friendly. So now we move on to the case of machine learning, which is in many ways different from software engineering. The main difference is made by the process of model training. So not only does the model training phase require special hardware, like GPUs or, for example, TPUs, but it's also related to this very compute heavy compared to traditional, for example, web development. So we utilize a lot more resources and a lot more intensely when training machine learning models than we do in traditional software engineering. Another topic that is special to machine learning is, of course, the data storage and dataset and data engineering aspects, which are very salient. But then again, we also have similarities. So for example, model consumption can be designed in a very similar way to software. So for example, you can have a machine learning model that is consumed over an inference endpoint, for example, just over TCP. And then there's also one of the new interesting topics in this field is the idea of tiny models and edge, for example, on very small hardware devices when you want to have, for example, machine learning models living on cameras or accessories or things like this. And that also is a call for optimization. So as I mentioned, I'm working as a machine learning engineer at the company called Valohai. Valohai is a deep learning platform for data scientists who are focusing on solving complex machine learning problems, usually deep learning problems, and especially these kind of problems that have that don't have ready-made solutions, or you can't like customize ready-made models. And every month, over 100,000 machine learning models are being trained on our platform. And this is only counting the ones that are using cloud compute. So we also offer on-premise compute. So the numbers are even larger. And when we are working with this amount of training, it naturally kind of leads to us having opportunity to really bring attention to this aspect of carbon emissions and climate impact of models. So inspired by my friend who is looking for carbon neutral data analytics products, I started this journey to find out how much carbon dioxide emissions it actually produces to run a given machine learning model training via our platform. The first challenge that I faced was that most of the cloud providers, AWS, Google Cloud, Azure, they all have started publishing information about your infrastructure carbon emissions, which is very great. It shows that there is a demand for this topic. And here is the picture that is in AWS in internal kind of a documentation of this feature. The challenge here is that there is a business goal in publishing this information, and the business aim is not necessarily to be as transparent and as clear as possible, but maybe to show how good the product is environmentally. And this leads to this field of a plethora of compensation. So as I said, over 100,000 models being trained monthly on our platform, a lot of traffic going via our servers over our APIs. And when we take a look at the emissions from the AWS console, this is how it looked. So according to this graph, in 2020, there has been some emissions going on, and after that, there has been none. And initially, I thought that there must be some kind of bug in the system or some other technical challenges, but it turned out that the reason the graph looks like this for us is that the majority of our infrastructure is hosted in this zone called EU West 1. And EU West 1 happens to be one of AWS carbon compensated regions. So technically, there are no emissions because AWS is offsetting those carbon emissions for us. Of course, this is very great. This means that we are, in one way, we can maybe say that our infrastructure is carbon neutral. But the challenge is also to kind of understand really what is behind all of this and how does this compensation work? Is it actually completely compensating for this, or is it kind of, should we be doing something more? But here comes the first tip, and it is if you're using cloud compute, you can select carbon compensated compute. You can select it by region. Both AWS and Google Cloud have some regions that are entirely carbon compensated. So do make use of those if possible. But keep a little bit of a critical thought also in not being completely blind to the emissions that kind of exist in the background. So moving onward, let's look a little bit deeper into what carbon emissions of compute actually are. When we talk about these greenhouse gas emissions or carbon dioxide emissions, we can use this thing called the GHG protocol to understand better what these different parts of the emissions are. So in this protocol, we divide the emissions of a product into 3 scopes. Scope 1 being the direct emissions from, for example, the company facilities, and scope 2 and 3 being indirect emissions, 2 being from electricity that is purchased, and 3 being from for example, capital goods and purchased goods and services. In the context of a data center operator, scope 1 would be, for example, the natural gas and diesel that are being brought to the data center in order to keep it going. Scope 2 then would be the purchased electricity, and scope 3 would cover the server hardware and also the construction of this server halls. So if we now look more detailedly into the scope 2 emissions, so electricity, when we are using computers or servers, the main impact in how much electricity is being consumed is from the processor load and the memory usage. This is also the reason why optimizing your code plays a big difference in green code or green machine learning as well. So if you're familiar, for example, with complexity analysis or, for example, big O notation, it's worth it to sometimes, both in reviewing and also in building the code yourself, think if you can optimize it in some way. Think about how it is utilized. Because especially when you're running multiple trainings, the training is iterative, this small kind of extra compute loads sum up and become a lot of waste. Then when we're looking more detailedly into electricity, we look at the region where this electricity is being produced, as well as the data center setup. So one of the terms that comes in handy when looking at the data center is called PUE, or power usage effectiveness. And PUE is basically used to describe the amount of electricity going to power servers compared to the amount that is going to power everything else in the data center. So the calculation of the power usage effectiveness is the total power in divided by the power used by the servers. And the optimal value in this case is 1, because we would like to have all the power that is going into the data center being directly used by the servers, instead of, for example, having a very wasteful cooling system where there would be a lot of electricity going into that. So when we look at average data center PUE values in, I think, 2018, the US average of older data centers was around 1.7, whereas Google reports as impressive numbers as 1.12. And as this comparison shows, there really is a big difference whether you're using this hyperscale cloud compute, contrary to if you have your own kind of a little bit outdated data center going about in your back storage room or something. So this is one of the tips I also have. If the nature of your data permits, I would recommend using cloud compute. Of course, I'm aware of, for example, privacy issues or GDPR issues with possibly sharing this data if it's especially medical data or something other very sensitive. But due to this effectiveness of data centers, using these hyperscale centers is really a good way of optimizing your electricity usage. Another concept that comes in handy is the electricity carbon intensity. So basically how many grams of carbon dioxide or carbon dioxide equivalent is produced in generating 1 kilowatt hour. And as you can see from this map is from Our World in Data in 2021. There is really big differences between the different regions in how green their electricity is. So based on this map, for example, if you are located in Europe and you're looking to use some data center in Europe to do your compute, you could, for example, select some data centers in, for example, Sweden, where the carbon intensity of electricity is lower. So in this way, by choosing kind of greener or more regions where electricity is less carbon intense, you can also contribute to the greenness of your model. So this is also one of my tips: choose greener regions if possible. And I was also checking, because I had one person ask me if you can see it in the price, if compute generally, for example, in Sweden would be more expensive than in kind of regions with more carbon emissions, and I couldn't find a difference. But of course, there might be some price differences, but I don't think you need to do a price trade-off in this case if you're able to select something in relatively close by. So then, how much electricity is the machine itself consuming? If you are familiar with, for example, using Mac or Linux, you know that there are some programs that can be used to measure their electricity consumption at the given moment. For example, stats in Mac or PowerTop on Linux. And now we would like to know, for this server that we're using for our machine learning training, at the given load of CPU, how many kilowatt hours is consumed during an hour of training? The challenge here becomes that these cloud provider or cloud instances of computers are often behind a heavy load of virtualization. So you can't really follow the bare metal resource consumption similarly to how you could if you would just be using a server that's sitting on your own table. So I'll present this case about how this team from Teads Engineering dealt with this issue. So Teads Engineering is a company who decided to build for their own internal purposes this data set of EC2 electricity consumption. And the process that they went by was that the first conclusion that they made was that AWS instances can be mapped to hardware directly. If you are familiar with AWS compute instances, you know that, for example, in the P3 family, 8x large has exactly half of the resources, the physical resources of a P3 16x large, etc. So you can kind of calculate out how the resources are divided by these different instance types. The next step they took was that they went to use AWS bare metal instances, so instances that expose more of the bare metal API, in other words, that aren't virtualized in the same way as the other instances. And there they were able to use tools like, for example, Turbostat to generate load and measure the electricity consumption at various load levels. And from there, they took the results of those resources and mapped them to the corresponding virtualized resources. And from there, they were able to generalize some assumptions of the electricity consumption of all the different other instance types. And this is the resulting dataset. You can all go and check it out at Teads Engineering carbon emissions, EC2 carbon emissions dataset. It's very interesting, and it has a lot of different detailed information on these different electricity consumptions on different load levels. So from here, we move to the third scope, which is the manufacturing scope. So what was interesting about the Teads Engineering dataset was that they also took into account manufacturing emissions, which is something that oftentimes is convenient to leave out. And as Udit Gupta and his team found, the majority of these data center carbon emissions actually may come from hardware manufacturing. So not just measuring the electricity consumption is not enough. So the strategy that we can take when measuring manufacturing emissions is that we divide those emissions up per component. And this is one of the things that the Boavizta team has been doing. So there is this hardware emissions dataset called the Boavizta hardware emissions dataset, where they have been listing not only rack servers, but also different types of personal computers, mobile phones, tablets, and their manufacturing carbon emissions. And they are also open to contributions. So please go and check out the Boavizta dataset on GitHub and follow their work. It's very interesting, and I hope that this will become more and more transparent, and also hardware manufacturers would become more and more open about sharing the emissions of the manufacturing process. So if we look at a case of AWS machine, and this is again looking at the Teads Engineering dataset, P4D is one of these EC2 accelerated compute instance families, and we're looking at its 24x large type. So this is something you could typically use for deep learning. So what we start with is that we define a minimal rack server, something that has one CPU and 16 gigabytes of memory, and that the kind of assumed emissions for that will be 1,000 kilograms of CO2 equivalent. On top of that, this specific instance type has 96 virtual CPUs. And from reading the instance description, we can see that the CPU type is Xeon Platinum. So from looking into that CPU's details, we can see that it's able to thread 48 parallel threads. And from this, we can conclude that it has 2 physical CPUs. So it has 1 extra physical CPU in addition to this minimal rack server. So we add the corresponding emissions for that. And similarly, we look through the memory, the GPU, and the storage, and add the corresponding estimated emissions for each of those components. And if you're interested in more of this, you can find very much more detailed information in the Teads dataset. So the amount of carbon emissions from the manufacturing process of this type of computer is 4,778 kilograms of CO2 equivalent. And usually this type of rack servers, the estimated lifetime for this type of server is around 3 or 4 years. And just to give you a comparison, in the US, the average carbon footprint of a household is 7,500 kilograms of CO2 equivalent per year. So in comparison to that, the emissions of one of these computers is in manufacturing of one of these servers is quite large. So the next challenge we faced, or I faced with measuring the carbon emissions of machine learning training was all the fuzziness that's related to this topic. It's very hard to estimate precisely the emissions when it comes to electricity, when it comes to virtualization, when it comes to measuring the manufacturing emissions. We just have to say that this is an estimation, and it's the best estimation we can give. As engineers, that's of course frustrating because we want the exact number, we want the perfect number, but that's just not realistic at this point in time. But as an outcome of this, we now have some estimations for machine learning model trainings that are run on AWS instances based on the Teads Engineering dataset, and we're looking forward to extending those emissions estimations also to the other cloud providers. One of the challenges that this kind of journey had not solved was the carbon emissions of object storage. Contrary to the emissions of EC2, AWS, or not the emissions, but contrary to the details of these EC2 instances and their hardware, AWS doesn't expose anything of the internals of its data storage services, including S3, which is what we normally would use for machine learning model training data. So what we do now is that electric or energy consumption of storage is relatively low. For example, 1 terabyte of SSD, the average consumption is only 2.2 watts per hour compared to, for example, this heavy-duty deep learning training server that can consume up to 3,782 watts per hour. But this is definitely something we want to look more into in the future. If you're interested in our emissions estimation system right now, you can go and check it out on GitHub. It's called Valohai Watson, and it's an open source repository. It's a Python tool. If you are using AWS Compute, you can absolutely use Watson with your project and get some estimations for your carbon emissions. And just as a kind of conclusion for this, as a summary of the different tips that I shared, my first tip for greener models would be that use some kind of MLOps solutions or cloud provider solutions that allow you to choose a region and a cloud provider for your compute power. You can also look into the possibility of using pre-trained or ready-made models if feasible, especially if you're starting up something new and you're not yet have any very complex, minutely defined needs. You can also make use of large-scale cloud providers to get the optimal power usage effectiveness value. You can also check if your training compute is carbon compensated. Ask your infrastructure provider if you're not sure. Also, showing them that you're interested in this is one part of this this kind of becoming more normal and becoming more of a interest in the field. You can try to measure the emissions of your training or measure the emissions of your infrastructure, because measuring is really the first step to optimization. And also assign time to work on code quality and optimizing code. Also keep this in mind when giving feedback on other people's code. So really reducing technical debt in one way is also a way of making your models or your code base cleaner. And also related to that, keep an eye open for stale and underutilized resources. For example, data sets you no longer use, servers you are kind of started some test project or test environment somewhere and just left it running. Maybe you want to set some reminders or warnings for those resources if you forget to delete them after you finished using them. And if we're looking into the future, maybe next we're probably as a community starting to focus more on the environmental impact beyond the greenhouse gas emissions. So for example, especially in manufacturing, really the mineral or metals or these materials that are being used and their impact on the local environment. We're also going to see a development of this detailed manufacturing emissions. So for example, this Boavizta dataset and try to get the more detailed description of, for example, these GPU and TPU manufacturing emissions. And also, I hope that we're going to see a normalization or standardization kind of the procedures for carbon compensation, so that we can really kind of understand better what different kinds of compensations there are and how they are working and how we should evaluate them. And this was really all I had for today. Thank you so much for having me, and I'd be happy to look at some questions if there's anything you were wondering about.
Thank you so much, Magdalena, for the awesome talk. As a programmer myself, at your topic, I'm pretty sure it echoes to quite a bit of people here. How we machine learning or like a coder, how we trying to get the best result at the same time. We need to step back and think about how we are how much power we're consuming on the GPU. So with that, we have a couple awesome questions. Let me try to get them all in as much as possible. Okay, so the first question is from Jean. Amazing question. It's about the AWS carbon compensation. So can you see about that compensation? Can you see a breakdown of how the carbon compensation is arrived at, or it's just a display in the graph that you show?
So if we look back at the, let's see if I can find the slide. So what they do is they don't show the original emissions. They just kind of reduce the compensated emissions from the original emissions. I know that AWS, if I don't misremember, they use this methodology of compensating that they they use unrenewable energy, and then they will, to compensate for that, instead pump renewable energy as a compensation into the grid in that area. So kind of putting in renewable energy to replace the non-renewable energy that they were using. So yeah, but they don't show more detailedly what has been compensated and what not. They just show you that you don't have emissions. Yeah.
Thank you. So the second question, in the dataset and other website, is hard to track when companies use. Is it hard to track when companies use carbon offsetting? Also, do you sometimes feel carbon offsetting is used in a way to deal with the problem without solving it?
Yeah, so absolutely, I think that this is a really hard topic. As I'm not the expert in the field of environmental questions, it's really hard for me, for example, to estimate what the impact of carbon offsetting really is and how it works, and also like the whole social impact it has, for example, in those areas where land is being sold for this carbon compensation forest, for example. Yeah, so it's hard, and I didn't follow the first part of the question. What was that?
Let me see. So the first part of the question is, I will read the question first. So in the data sets and other websites, is it hard to track when companies use like carbon offsetting? So I assume, let's say if my interpretation would be like AWS has like graph showing, but like other websites might not. So
yeah.
So you have experience on that?
Yeah, these things can be found in the detailed product descriptions from the cloud providers, and there they usually explain also the methodology. So the information is available. It's not given to you for like very easily, but you can find it. And I would, if you are using, for example, Google Cloud as your main cloud provider, you can go and research how they are dealing with this topic, and they have a lot of, for example, video material and everything. So they do kind of talk about it, but they maybe have a little bit of this marketing marketing attitude in their way of describing these things, but they do share quite openly.
Makes sense. ESG is a very, very big thing right now in the globe and in general. Okay, next question is should be a little bit easier. So some of like our participant asked like the similar question. So well, first is like how do you end up how do you get your first job in ML? Also, if like they want to pursue as a new person who's like new in data science or like like what kind of resources for like sustainable ML DL like you could recommend to them so that they can learn more about it?
Well, I definitely recommend you try to understand. This is a little bit of the divide between data science and engineering, right? That classically data scientists have more of a scientific approach, whereas engineers, software engineers, ML engineers have more of an understanding of the actual computers, how computers work, the electricity happening inside the computers. So that's one topic. If that interests you, try to really understand like what a server is, how does a data center work, how do these different resources play together, and what are the kind of factors that are causing, for example, this electricity to be consumed. You can also try and measure the memory usage and also CPU load that your different kinds of code are generating. So just trying to kind of look under the hood into the computer is very helpful. Yeah.
That's good. Okay. Since we only have 3 minutes, like we started a little talk a little late. The talk a little late. So very last question. This person is asking, I wonder if the difference in hardware creation emission versus electricity consumption during the training has been tracked. Would it be greener if our MLOPs will be swapping more efficient hardware to more efficient hardware at different training steps, or if by buying multiple servers, the carbon emission overwhelms the electrical emission? So what can we do in MLOPs to make it greener, or it's just like a researching and setting up using a greener data center?
Yeah, so I would definitely, if your core product is ML and that's what you want to focus on, I would definitely just go to buy the compute from a cloud provider and then like let them take care of optimizing these things and let them take care of actually making sure that the hardware you are using is up to date and it's relevant and it's as green as possible. So kind of, really taking the support you can get from there and also showing, for example, the community of developers working at these cloud providers that you are interested in the carbon emissions, you're interested in the manufacturing carbon emissions, you want to use greener servers, you would like to see how they are, for example, compensating for this electricity, and let them do the background work for that, rather than kind of worrying about, oh, did the server I bought 6 years ago, should I buy a new one or should I not? Because when you have those things at such a large scale, as for example Google Cloud has, it's so much easier to manage the whole equation of what you have and when it's time to renew them and what the kind of cost of that is and how to calculate the lifespan of them, for example. Yeah.
Thank you very much. So I guess I see many other great questions. But unfortunately we are on 1 minute off from the end time. I will recommend you guys go to Magdalena's LinkedIn, add her. Definitely ask her the question. I really personally really think this is a great topic. This is a really important issue as machine learning and data science is really growing like dramatically. So please add her. and like discuss the topic. And I really love your data scientists as well, so it is something like we echo, like I said. So I think that's it. So just want to thank you again for Magdalena for the great presentation. I learned a lot today from you, personally. So we hopefully everyone is enjoy the rest of the day for you guys for your time, and then enjoy the other talks.
Yes,
Thank you
thank you, and thank you,
guys.
Aaron. See you.
Thank you. See you. Bye.
Bye.